Today we're building a lock-free ring buffer, one of the fastest inter-thread communication patterns ever invented. This is the core algorithm behind the Disruptor, which processes millions of events per second in financial trading systems. We'll use atomic operations, compare and swap, and memory barriers. All in a single Java class under 200 lines. We declare a generic ring buffer. The buffer is a plain Java array that will hold our items. Capacity must be a power of 2, this lets us use bitwise and with mask instead of expensive modulo operations when converting sequence numbers to array indices. The mask is capacity, 1, so for capacity 8 the mask is 7, binary 0 1 1 1, and sequence 7 gives us the array index. Instead of tracking array indices directly, we use monotonically increasing sequence numbers. Both cursors start at -1, meaning no items have been produced or consumed. The producer cursor tracks the last published sequence number, the consumer cursor tracks the last consumed sequence number. These are atomic long so multiple threads can update them safely without locks. Modern CPUs cache memory in 64-byte cache lines. If two variables that are frequently updated by different threads sit in the same cache line, they cause false sharing, each thread invalidates the other's cache, destroying performance. Adding in used padding fields before and after the cursors pushes them into separate cache lines. This is exactly what the Disruptor does. The constructor validates that capacity is a power of 2 using integer.bitCount. A power of 2 number has exactly 1 bit set, so bitCount returns 1. We store the capacity and mask, then create a generic array. Java doesn't allow new capacity, so we create an object, and cast it. The @suppress warnings, unchecked, silences the inevitable compiler warning. This cast is safe because the array is never exposed outside this class. Publish uses a compare and swap loop. We read the current producer cursor and calculate the next sequence number. We check if the buffer is full. If the distance between producer and consumer exceeds the capacity, there's no room. Then we attempt to atomically advance the producer cursor using compare and set. If another thread changed the cursor in between, the CAS fails and we loop again. This is lock-free, no thread ever blocks waiting for a lock. After successfully claiming a slot, we convert the sequence number to an array index using nextProducer mask. Because capacity is a power of 2, this wraps around correctly. For example, with capacity 8 and sequence 8, 7 is equal to 0, wrapping back to the start. We write the item and return true. The ring buffer pattern guarantees that no consumer will read this slot until the consumer cursor reaches this sequence number. Consume mirrors publish. We read the current consumer cursor and calculate the next sequence. We check if the buffer is empty. If the next consumer sequence is beyond the producer's position, nothing has been published yet. Then we atomically advance the consumer cursor using CAS. Again, this is lock-free, multiple consumers can compete for slots without blocking. After claiming a slot, we read the item from the array, set the array position to null to allow garbage collection of the consumed object, and return it. Setting to null is important in long-running applications. Without it, the buffer would hold references to consumed objects indefinitely, causing a memory leak. Size returns the number of unconsumed items by subtracting the consumer cursor from the producer cursor. Because cursors are monotonically increasing, this always gives the exact count. Is empty and is full are convenience methods. All are thread safe because they read atomic values. We create a ring buffer with capacity 8. A countdown latch with count 2 will let us wait for both threads to finish. 2 atomic integer counters track how many items were produced and consumed, will verify they match at the end. The producer publishes 20 messages. If the buffer is full, it busy waits with thread.yield. In a real system you'd use a wait strategy like locksupport.parknanos. After publishing, it increments the counter, prints the message and buffer size, then sleeps a random time to simulate real work. When done, it counts down the latch. The consumer runs until both the producer has finished and the buffer is empty. If no item is available, it yields. When an item is consumed, it increments the counter, prints, and sleeps. The condition latch.getCount, 1 means the producer hasn't counted down yet, so there might be more items coming. Both threads start. Latch.await, blocks until both count down. Then we print a summary showing the number of items produced and consumed, and whether they match. In a correct lock-free implementation, they should always match, no items are lost or duplicated. We've built a lock-free ring buffer using atomic operations and compare and swap. This pattern is at the heart of high-performance systems like the Disruptor, which processes 6 million transactions per second. Understanding CAS loops, false sharing, and sequence-based indexing gives you the foundation to build ultra-low latency concurrent data structures.